Today we're going to be talking about the Diels-Alder reaction. It's a really useful reaction for putting a whole bunch of complexity into a molecule. It is a carbon-carbon bond forming reaction, so it's a definite important note card to be talking about. So keep in mind, anytime we do a carbon-carbon bond forming reaction, that really should be in a separate kind of category that is really important, because these are the types of reactions that are done synthetically to build drugs and well, medicines and such like that. So anyway, what is the Diels-Alder reaction? What are the different parts of it? Well, first of all, it is going to definitely involve some sort of diene, right? So here's a model of a diene. And so let's kind of do something special to this thing. And what we're going to do is we are going to rotate around that single bond to start off with. And so when I do that, keep in mind, I'm going to have to be breaking the that kind of like delocalized system, right? And so there is an energetic cost to this. But the good news is it is still, mostly a single bond. So I can do a rotation like this. And you'll notice that I've put the dienes, or sorry, I put both of the enes kind of on the same side of these carbons, right? So they're on this same side. So those two different conformations are going to become important in just a second, right? This is called an S-trans. Keep in mind that S corresponds to the single bond, right? And so this is called S-trans. It turns out the Diels-Alder reaction, if you're the diene, you need to be able to get in what's called an S-cis conformation, right? And of course, this is different than the cis and trans that we talked about with double bonds, but each of these could also be a cis or a trans. So specifically what we're talking about when we say that this has to be S-cis is this bond has to have the diene kind of pointed in this particular direction. So let's draw that. And we're going to start off, and we're not going to have any kind of substituents on here, but another really important thing that we might as well talk about generally right now is the Diels-Alder reaction is not only is it important because it's a carbon-carbon bond former, but it is a reaction that is regioselective, and it is also stereoselective. Keep in mind, reactions that have these characteristics are also really important. So we have something that is a carbon-carbon bond former, something where we can get really specific regioselectivity, which we'll probably talk about in a future lecture video, and also stereoselective that we'll talk about in a future video lecture. So it's good to keep that in mind to start off with. So this is the diene. It's a pretty boring one with no substituents on it. And then, of course, you also need another part in order for this reaction to occur. And that other thing is some sort of multiple bonded species, right? And for ease, I'll just highlight the just an alkene here with whatever happens to be bonded out here. And this, in a Diels-Alder reaction, is called the dienophile. Right? The diene lover. And it turns out that these groups right here, I can't really properly do a Diels-Alder reaction unless I put something really specific in there. And just to make my life easier, I'm going to put it in both places, right? And that EWG is an electron withdrawing group, right? And so throughout our discussions of Diels-Alder chemistry and eventually when we get to aromatic chemistry, we're going to be talking about these groups that overall, either through induction or through some sort of resonance effect, will withdraw electron density from a compound. It turns out that just about every Diels-Alder reaction, if it's a normal one, requires at least one group that is electron withdrawing. This includes things like halogens, like carbonyl-containing compounds, and we'll start to see that again when we start to talk about some of the regio and stereoselectivity of this reaction. But there's a really important arrow push here that maybe I'll do in red, because I've been doing my arrow pushes in red. And what's going to happen between this diene and dienophile is what's called a paracyclic reaction, which we've seen a little bit before. Like, for instance, an ozonolysis does a paracyclic reaction. And what will happen is this door will swing out, just like we've seen before, and it'll attack that kind of the terminal carbon there, and you'll see a push of arrows that looks like this. So these 3 arrows, if you follow the result of them, we end up with this 6-membered ring where there is a double bond right here, right? And that's one thing that is often noticeable about a Diels-Alder reaction, right? You'll find that a 6-membered ring forms from nowhere, and then wherever you formed like another multiple bond is usually on the opposite side from wherever your dienophile attacked. And so let's just kind of put those electron withdrawing groups in there. And when we start talking about the stereoselectivity, we'll find out that those electron withdrawing groups have to be oriented in a really particular way. So keep in mind, right, this is the minimum of what's required in a Diels-Alder reaction, right? You need to have a diene of some sort, you need to have a dienophile of some sort, and there has to be some sort of electron withdrawing group on at least one of these carbons. And then we form this 6-membered ring. And so one thing that we're going to work a little bit on is our various synthetic strategies for kind of knowing when to do the Diels-Alder reaction. And so the important thing, and let's see, I'll use blue for this guy. The important thing when we're doing that kind of retrosynthetic analysis, or in other words, we look at a product and are trying to figure out ways that product could have formed, it's really important that we're able to see that 6-membered ring that's formed. And then we can kind of put all the different pieces together, and we will notice that this multiple bond right here, that must have been where we've had, that'll kind of help us to locate the carbons of the diene, right? And so that means that the new bonds that were formed were right here, right? And so you find that little 4-carbon piece based on the location of that double bond, and then you can also kind of back this out, and you can recognize what you might have started as to get this ring to be built. Of course, this one is really simple, not that hard to see, but this kind of analysis is going to be an important one eventually. So now that we've talked a little bit about the requirements for this dienophile, let's talk a little bit about the requirements for this diene. Right? And so I do have a model kit here. So here we have our diene. Here's our dienophile. And what actually happens, even though it kind of looks like the way I've drawn it, things are coming together like this, it's more like this thing is less like kind of Pac-Man eating the ghost, if that is a reference that makes any sense anymore, and more like what's really happening is the pi orbitals that make these things up are kind of making a sandwich, right? And it turns out that the requirement for these electron withdrawing groups, first of all, is going to take electron density out of this thing so that we can actually bond to electron density in this other thing. But you'll notice that I made a point when I did this reaction to flip it around such that those electron withdrawing groups are kind of like inside the sandwich as opposed to outside the sandwich, right? I didn't do this, right? And it turns out that those same electron withdrawing groups, especially when is it really common that they themselves have some sort of pi orbitals, that's going to be a requirement for this reaction to happen properly. And when that happens, right, and you'll see kind of an animation of this eventually, possibly this video, and when those bonds form, this sandwich kind of does this kind of thing, right? And so there's kind of a rehybridization that causes this to happen. And so the product, right, here it doesn't necessarily matter because there's no groups out here that really, these are just H's at this point. But this kind of transition state where these things are kind of pointed down and away, right? This is going to lead to something called an selectivity in the Diels-Alder reaction, right? And I just mentioned that now because these model kits can be really, really helpful. And so in a sense, I always thought about this just because I was kind of a Atari dork back in the day, right? Where I always think that Pac-Man needs to have like the meaty stuff like kind of going into his mouth, right? As opposed to this. And honestly, like people tried to explain it a ton of different ways, and that's the only real way that made sense to me, right? And so what ultimately happens is I end up with that 6-membered ring where these guys are, at least the way I'm holding it right now, pointed back, right? I don't end up with what's called the exo product where they both end up pointing up, but this will be a little bit clearer once we start to talk about stereoselectivity. So, as I promised, we're going to talk a little bit about requirements in this dyeing, and hopefully these model kits will help me a little bit. So, the requirements for the dyeing, remember, of course, that that S-cis form is necessary, right? I need to, if this thing is in a trans orientation, right, I need to be able to do this in order to make the Pac-Man that's ultimately going to get my Diels-Alder reaction to happen, right? It turns out anything that I do to this that make that transition harder, the less and less likely and the slower and slower the Diels-Alder reaction is going to go. So it's typically the case on a test question or something like that you'll be given a dyeing that's not in the right orientation, and you have to kind of mentally do that rotation right there. So what kinds of things is going to make an S-cis form maybe less likely to happen? Well, sterics, right? That old thing that we've talked about a bunch turns out to play a huge role. Now, as I do this, right, you'll notice that Pac-Man is, not that unhappy right now, right? But I'm going to change this from just a simple 1,3-butadiene into something that has a couple more methyl groups, right? So here's my S-trans form, and what I'm going to do is I'm going to put these methyl groups on the last carbon in a really particular manner, right? And so I'll do that. And so what you'll notice is that this guy right here, relative to that double bond, right, that's a Z orientation, right? The bulkier groups are on the same side of the double bond, or you can think about it as a cis, right? Same thing over here, right? These guys are in a Z orientation, or you can think about it as a cis, right? And now watch what happens when I try to make this get into an S-cis form, right? You notice that those groups bang into one another, right? And so this is obvious steric strain, right? And so it turns out that something like this, which I'll draw in just a second, right, is going to be very, very slow and probably will not do any kind of Diels-Alder reaction, right? That's because of that inability to get to the S-cis form. All right, and so there is what's trying to be our dyeing in the Diels-Alder reaction. And it's typically said that anytime you've got these groups right here, especially if there's any kind of bulk to them, it makes it much, much more difficult to do a Diels-Alder reaction, right? You can also have like questions of degree where like you have a big giant tert-butyl group out here and then maybe even just an H right here, and that's going to be a pretty slow Diels-Alder reaction. But it turns out that kind of confusingly stated, but that cis on both sides of your dyeing or for both of your alkenes is going to be something that's really problematic. Another thing that can sometimes happen, which I guess I don't necessarily have to draw this, but we can just talk about it, is another way that I could get this S-cis form as not being able to form is if I did something crazy like I made a ring out here that kind of like holds these sides together so that it's really, really hard for this thing to kind of to move down, right? So that's something that you'll often see where if I were to do something like even put a ring right here, right, that's going to be really difficult for that thing to get in any kind of like S-cis form, right? Because you're linking these things back. Right, so hopefully that makes some sense. Right, so there's an example of something that would really struggle to do a Diels-Alder reaction.
So all the requirements, oh, by the way, I should probably label this. Right? So these are all the requirements for diene. Another thing really helps out this reaction, that electron donating groups often help a diene to react, right? And so it's kind of that yin and yang, right? In the diene, you want electron donating groups, and then you want electron withdrawing groups in the dienophile. So electron donating groups are going to be things like alkyl groups. They're going to be things like oxygen species, believe it or not. Right? So ethers and alcohols are going to be really helpful for this thing. Also turns out that amines are also really good at being electron donating groups. And when we get to aromatic chemistry, this might be kind of counterproductive, right? We know that oxygens and nitrogens are really electronegative, so you might think that they'd actually be electron withdrawing, but it turns out they're not for reasons of resonance. They actually, by resonance, can donate these electrons into the ring, and that actually kind of overcomes their inductive withdrawing effect, believe it or not. So you'll typically start to see reactions like many on your homework and such that have these groups arranged and in the diene, and those are electron donating groups. Since I gave you a list of electron donating groups, it might be good for me to at least end this with talking a little bit about electron withdrawing groups. So these are going to very commonly be things like halides, right? X representing anything in the halogen family. It's really common with electron withdrawing groups, things that are carbonyl based, right? Either, say, a carboxylic acid, and there's the ring, say, where R is an OH for a carboxylic acid, or an ester, things like that. And another really common way of getting an electron withdrawing group in there is something like a nitrile, right? And so when we get to the next video lecture, you'll be seeing quite a bit more about this. So that's just a real brief introduction to Diels Alder reactions. We're going to be talking the next time around about stereoselectivity and regioselectivity in these things.